We're now going to cover the interpreter pattern. In this discussion, you'll learn what the interpreter pattern is and how it works, how it's structured. You'll also learn to recognize how the interpreter pattern can be applied to automate the flexible processing of input expressions from users in the Expression Tree Processing app. The purpose of using the interpreter pattern is to process user input expression, build a parse tree, and then use this parse tree later to build the corresponding expression tree. In this discussion, interpreter will be applied to automate the parsing of input expressions from users. Let's first provide a little context for this in the Expression Tree Processing app. This app can receive user input from a variety of different sources: the command line, user interface, buttons, text views, and so on. The input can also arrive in a variety of formats. For example, it can be in pre-order or post-order, level order, in order, and so on. We don't want to have to require the users to manually program this input. That would be incredibly tedious and error-prone. New input expressions shouldn't require writing and compiling and linking code. When we looked at the bridge pattern implementation earlier and the composite pattern implementation earlier, you'll note that everything was hard-coded. We hard-coded the creation of the various expression tree nodes that were used to build the expression tree. But that's clearly not going to work in practice. We also would like to make it to be the case where we don't have to change the existing client code when new types of input expression formats are added. If we have support for in-order expression formats and then we add support for new different types of formats, we don't have to change anything in our application. That should all be hidden from the bulk of the client code. So what's the solution? We're going to create an interpreter to automate input expression processing. This is going to work as follows. We're going to create an interpreter object that will process user input expressions and create the corresponding parse trees. So when an input expression comes in, the interpreter takes that and creates the parse tree. And then later, we're going to build the expression tree from the parse tree itself. For this particular discussion, we're going to focus on the interpreter's role in building the parse tree. And then in the next video, we'll talk about how we're going to use the builder pattern to take that parse tree and create the corresponding expression tree. Here's a bit of the overview of what the interpreter class could look like. We're going to use it to transform the user input expression into the parse tree. And to do this, we're going to have several methods involved. There's a couple of hook methods we're going to use to help optimize and generate the code in a more flexible way, a more open-ended way, using some other patterns we'll talk about shortly. And then we also have our main interface method called interpret, which is going to take the string provided by the user, either through a command line or a GUI or something else, and it'll be used to actually control the interpretation steps to build the parse tree and then later the expression tree. To help out with the processing and parsing, we're going to also have another class called the symbol table, and this will play the role of the context, and we're going to use this to implement setters and getters for various types of leaf nodes. In our particular case, we're going to use this to be able to name expressions so we can use them as opposed to simply having to write everything as constants. We can also have variables as well. From a commonality and variability point of view, the interpreter is going to provide a common interface for building parse trees and expression trees from user input expressions, but the actual structure of how these trees are implemented can vary in a very seamless and uniform way, depending on the input format, the contents of the tree, and any type of optimization or semantic analysis that might be performed on the input expressions. This particular way of arranging the code follows nicely on the Gang of Four interpreter pattern. The intent of this pattern is to take a language and then define a representation for its grammar and create an interpreter that uses the representation to understand or interpret sentences in the language. That's a bit of a mouthful. What it's really saying is that you're able to read input in terms of expressions or programs and whatnot, and the interpreter will do the appropriate thing to translate and transform it in some way corresponding to the grammar that represents the language. You would typically apply this pattern under a couple of circumstances. One, when the grammar for the language is simple and relatively stable. And secondly, when time and space efficiency is not the primary concern. If those things don't apply, you may want to look at alternative approaches for doing parsing and interpretation. And we'll talk more about those when we get into the implementation section. But first, let's talk a bit about the structure and participants. As you can see here, we have a couple of different pieces. We have the interpreter, which is going to be a client, which is going to be used to guide the way in which this is all taking place. We have some context. In our case, that's going to be implemented using our symbol table. And then we have various types of abstract expressions. These will be things we call symbols. We have terminal expressions, which we're going to be representing by numbers or variables. And finally, we also have non-terminal expressions, which we're going to use to define various kinds of operators like add, subtract, multiply, divide, unary negate, and so on and so forth. Let's now go ahead and talk about how we could implement the interpreter pattern in Java. We'll create a class called interpreter with a method called interpret that takes an input expression that's a string from wherever we get the user input from, command line, graphical user interface, or whatnot. This particular method will be implemented as a template method, which is another pattern we'll talk about later on in this series. There are 3 hook methods part of this template method. The first one, build parse tree, parses the input and creates a parse tree. Assuming anything is actually created, the optimize parse tree method, which is optional, can be used to optimize the parse tree, perhaps reducing common sub-expressions, constant folding, other kinds of operations that might be very useful. And then the final hook method is something called build expression tree. And this takes the output of optimized parse tree and creates an expression tree from it. Here's a bit more detail on how things work. The build parse tree method creates a parse tree, which in our case will simply be a stack of symbols, where symbols are what are going to be used to keep track of the various kinds of operators and operands that we're seeing as we're parsing the input. We then go ahead and take a look at each element in the input string, one character at a time. If it's a number, we go ahead and handle that. If it's a variable, we handle that. If it turns out it's an operator, like a plus sign or a minus sign or a multiplication sign and so on, we go ahead and handle that. And every step along the way, we parse the input by looking at the type of symbol, terminal symbol, non-terminal symbol, and so on, and create the corresponding element in the parse tree. What we're going to do now is we're going to move to the editor, and I'll show you some examples of some of the classes and methods that are part of the interpreter implementation in Java, so you can get a better feel for how we can implement this pattern. The implementation of the interpreter pattern resides in the interpreter.java file. If you take a look at this file, you'll see that there's an interpreter class that contains a number of data members, methods, and various nested classes that implement both the interpreter and builder pattern implementations for the expression tree processing app. Let's go ahead and take a look and see how the basic interpreter works, and then we'll talk about the builder portion in the next video. The entry point to the interpreter class is a method called interpret. The interpret method takes an input expression as a string. This corresponds to something like -5 times 3 plus 4, or whatever the user has entered. The interpret method itself is implemented as a template method. We'll talk more about the template method pattern later. There are 3 main steps in this template method, which are easily extended by subclassing from an interpreter. The first step is to build a parse tree from the user input expression. Assuming we actually get anything as part of that, assuming that there was a valid input, we can then optimize that parse tree, which is an optional step. And the third part of the template method is to build the expression tree from the parse tree. We're going to focus in this discussion just on building the parse tree. When we talk about builder, we'll discuss how to build an expression tree from the parse tree. So let's go down and take a look at build parse tree. Here's the build parse tree method. The build parse tree method starts by creating a stack of symbols. Let's take a quick look and see what a symbol is, because that'll help to understand how all the other pieces fit together. Here's the symbol class. The symbol class is an abstract class that defines the data structure that's at the core of the parse tree. Not surprisingly, we're going to end up subclassing symbol for the different kinds of elements that correspond to what's in a parse tree. Things like numbers, the add operator, the multiply operator, and so on. There's a number of fields in this class. We keep track of the precedence. We keep track of the left and right symbols in case these are composite symbols. And we also define a couple of helper methods, one to access precedence, one to add precedence. And the most interesting method, which we'll defer to the builder discussion, is a method called build, which converts this symbol into the corresponding type of component node, which is used as part of the expression tree itself. So let's go back and take a look at how the actual processing takes place. For every character that's in the input expression from the user, we're going to call the parse next symbol method in order to process that symbol and create the appropriate updates to the parse tree. So let's take a look at parse next symbol. Here's the parse next symbol method. As you can see here, what it does is it takes a look at each character and tries to figure out what kind of element, what kind of number or variable or operator we're seeing at this point. For example, as we come along and we find that we've got a digit, then we're going to go ahead and treat that as a number. So that's handled in this particular case. Likewise, if we find ourselves with a letter, this means that we're actually processing some type of variable. If we see the plus operator, the symbol for plus, that means we must be creating a new addition operation. So let's take a quick look and see how that works. As you can see here, what we do is we go ahead and create a new add object. Let's take a look at add. Add is a subclass of operator, which itself is a subclass of symbol, and this corresponds to all the different kinds of arithmetic operators we support: addition, subtraction, multiplication, division, and so on. The most interesting method we're going to just touch on here just for a moment, we'll come back to later, is the build method, which is used to create the appropriate corresponding type of composite add node that relates to an add operation. We'll come back and look at that later. In addition, we also keep track of precedence that we're going to use here in order to figure out how to parse the input based on the precedence levels that we've defined as part of our grammar. Same kind of behavior takes place for subtraction, multiplication, and so on. And every time we find one of these operators, we go ahead and we insert the symbol by its precedence into the parse tree. And that particular processing is used to make sure that things get in the right order in the parse tree corresponding to their precedence. Let's take a look at insert symbol by precedence. Here's the insert symbol by precedence method. Essentially what it does is it takes a look at the precedence of the symbol that's being inserted as well as the parent precedence, and it figures out how to rearrange the tree accordingly. By the time we're all done processing all of the input, we're going to end up with a stack that has a single item in it, and that item will correspond to the root of the parse tree. And all the other parts of the parse tree will be hanging off the left and right child of that root using the symbol hierarchy in order to be able to keep track of those relationships. Now that we're done looking at the actual code, let's talk about some of the consequences of applying this pattern. Some of the benefits are that simple grammars are relatively easy to develop, change, and extend. All the rules are represented by distinct classes in a consistent and orderly manner. The particular grammar we're showing here removes left recursion, which makes it easier to parse by hand. Another nice consequence is that adding another rule simply adds another class to our implementation, so that makes things fairly straightforward to apply. There are some downsides, however. If you start trying to apply this pattern to a very complex grammar, say a grammar for Java expressions or C and C++ expressions, you'll probably discover that you'll end up with lots and lots of classes, lots of rules, lots of interdependencies, and so on. So if you're in that kind of a situation where you're really trying to do complex things, you might want to consider using a different approach, such as a parser generator, like Antler or Lex and Yak or Bison and so on, which are more scalable and work by using a different paradigm altogether. Rather than writing the code to do the parsing and interpretation by hand, instead you describe things in a formal grammar-like syntax, and then there are various ways of having the parser generator create lookup tables that do the syntax-directed parse of the expressions or the language you're trying to process. There's a variety of different ways to implement this pattern. As we mentioned before, one approach is to define different language rules, one per class. For example, literals could be translated as terminal expressions, things like numbers or variables. Likewise, you could have binary and unary nodes expressed as non-terminal expressions. One of the consequences, of course, is you can end up with a large number of classes, but the classes mimic the grammar. So as long as the grammar is fairly understandable, the class design will also, hopefully, be understandable as well. An alternative approach, which is actually what we use in our implementation, is to create a class that uses the precedence of the operators and operands to build a parse tree of symbol objects by using a stack. And if you take a look at the implementation, that's what we're using here. This approach ends up with fewer classes, but the design doesn't quite as clearly mimic the grammar. Both approaches are perfectly valid implementations of the pattern, just that one is more directed towards the class rule structure, one is more directed towards the precedence of operators and operands. There's a number of different known uses of this pattern. Various text editors and web browsers implement interpreters in order to lay out documents, check spelling, and so on. TeX and LaTeX are good examples of things that work this way. Some of the earlier compilers for languages like Smalltalk used interpreters implemented using this pattern. The Gang of Four book talks about regular expression parsing using this particular approach and so on. So it's not an uncommon way of designing and implementing interpreters. So to summarize the pattern, we use interpreter to automatically convert input expressions into a parse tree, which is then used subsequently to build the corresponding expression tree. And next, we're going to cover a creational pattern, builder, that completes the interpreter by actually generating the expression tree from the parse tree.